Today I'm going to be talking about how manganese and zirconium rely on each other to stabilize the microstructure within aluminum copper alloys. The theta prime precipitate with an aluminum 2 copper stoichiometry and a very high aspect ratio is responsible for aluminum copper alloys hardness. This precipitate has coherent interfaces as well as two four-fold symmetric semi-coherent interfaces and therefore has an octagonal prism-like shape. Unfortunately, the theta prime precipitate is metastable and eventually transforms into theta, which coarsens rapidly and decreases the hardness of the material. Oak Ridge National Laboratory has recently developed an aluminum copper manganese zirconium alloy deemed ACMZ. This alloy retains its hardness all the way up to 350 degrees C after a 200-hour exposure. The important and critical solute additions are manganese and zirconium. Atom probe tomography results of a 300 degrees C 200-hour exposure reveal that zirconium segregates to the coherent interfaces, while manganese segregates to both the coherent and the semi-coherent interfaces, with additional segregation to the semi-coherent interfaces. Density functional theory and phase field simulations have shown that interfacial energy reduction as well as solute drag effects increase the stability of these precipitates from this solute segregation. Hardness results of alloys with sole manganese additions reveal that manganese stabilizes the microstructure only up to 300 degrees Celsius. Alloys with sole zirconium additions do not stabilize the microstructure compared to alloys without zirconium additions. However, when you combine manganese and zirconium additions, they work synergistically to keep the hardness at 350 degrees C. Therefore, the comparison between the 300 and 350 degrees C temperatures is important to understand their synergistic effect. The APT results reveal that at 350 degrees C exposures, manganese no longer segregates to the semi-coherent interface, while at the same time zirconium and titanium continue to segregate to the coherent interface as they did at 300 degrees C exposures. Notice that these exposures were for 2,000 hours. The solute segregation behaviors at the theta prime coherent interfaces were compared using Gibbsian excess calculations. Several samples exposed to different temperatures and periods of time were used. The number of interfaces used in each Gibbsian excess calculation is shown in the legend. Titanium and zirconium continue to segregate to the theta prime coherent interfaces for all temperatures and times studied, while manganese does not continue to segregate to the interfaces for times above 1,000 hours at 300 degrees C. As titanium and zirconium continue to segregate to the theta prime coherent interfaces, the interfacial energy continues to reduce. Another thing to note is that titanium and zirconium are L12 formers, and about one plane of L12 structure is about 2 excess atoms per nanometer squared. STEM HADF imaging reveals that there is an L12 structure at the coherent theta prime interface. Density functional theory was used to calculate the interfacial energy of this new structure and compare it to the original coherent theta prime aluminum interface. As you can see that both sides of the L12 structure have a lower interfacial energy than that of the original theta prime aluminum interface, which is widely accepted as 200 millijoules per meter squared. Remarkably, the L12 theta prime interface has an almost zero interfacial energy, while that of the L12 aluminum matrix has an interfacial energy of about 50. Overall, the addition of manganese is necessary in order to stabilize the microstructure for a long enough period of time for the slower diffusing zirconium and titanium to segregate to the coherent theta prime interfaces and eventually form an L12 structure. The formation of the L12 structure further reduces the interfacial energy of the coherent interface and also creates a ledge poisoning effect, which ultimately further stabilizes this alloy. This is how the manganese and zirconium work synergistically to stabilize theta prime and aluminum copper alloys. These results have recently been published in ACTA-MAT and I'd like to thank you for your attention.